So first we have some physics news.
I think I figured out how to make this. Okay, so we're going to be reviewing a lot of the physics news from before, as it's going to tie in a lot with today's lecture. So the first one we're going to review is from a few weeks ago about the 2020 Nobel Physics Prize from Drs. Penrose, Genzel, and Guess. And it was from their work from black holes. And big investment in astrophysics. Dr. Penrose, he proved that the black holes must exist due to general relativity. And he also invented the Penrose diagrams to simplify the mathematical idea of general relativity, which is generally very complicated, as you've been seeing over the past few lectures. And they made key observations also, Drs. Genzel and Guess, that the dark monster in the center of our galaxy is actually a black hole. And so general relativity essentially curves and warps space-time, as Bohang was mentioning. It's a geometric property of space and time, and it also allows for light to be bent around large masses. Another news that we talked about is gravitational redshift, where strong gravitational fields can distort space-time as well. And there's actually a shift to the redder wavelengths. It's a shift at around approximately 2 millionth of a wavelength due to general relativity, which the researchers from the Institute of Astrophysics of Canarias, the Canary Islands, were able to measure that. And they were able to look at that. And they look like the position of iron lines in the solar spectrum. And you can see the source for that at the bottom. And this last one we're going to review is last week's news, which is the news on gravitational wave astronomy, which is the 39 events you can see by the LIGO collaboration and Virgo collaboration. LIGO is Laser Interferometry Gravitational Wave Observatory. And they published 3 papers. The catalog paper for detection of black hole and neutron stars. They published the populations paper for mass and spin distribution of black holes. And they have the testing general relativity paper, where they were able to show that general relativity passes key constraints from these solar masses. And at the right, you can see a visual of the solar masses. And in orange, you can see like the neutron stars. And in like blue, you can see like the black holes. And there's a source for that. And this article is published by Northwestern University.
Wait a second, let me share my the slides. Wait. Okay, let's get started. So in this session, we're going to be review general relativity, and then talk about some like black holes and gravitational waves. Relativity deals with space and time, but general relativity deals with the geometry of space-time, especially a curved space-time. And there isn't a gravitational force in general relativity, and all the gravitational force are just manifestations of the curvature of the space-time background. And Einstein's field equations are the core of general relativity. It describes how space-time and the relationship between space-time and large masses. And with the tool of differential geometry, general relativity is well formulated. Yeah. So let's move on. And we talked about the equivalence principle in general relativity. So it says there is no experiment that can be done in a small confined space that can detect the difference between a uniform gravitational field and equivalent uniform accelerating. So it's saying like there isn't a difference between like you can tell when you're stay on a surface of a planet, or you're accelerating in space, and all the local physics laws are governed by special relativity. And we talked about the gravitational lensing. So as Rohan just said, a light can be bent when travels around the large masses, for example, black hole or neutron star. And let's talk about non-Euclidean geometry. We know in Euclidean geometry, all the parallel lines never intersect and they are always parallel. And however, in non-Euclidean geometry, for example, Riemannian geometry, two parallel lines can intersect. For example, as you can see on the sphere, like two lines, even though like they are parallel. It's not showing in here, but if you, like two lines are parallel, but they will intersect at some point. For example, if you look at like two lines on the equator, they will intersect at the pole, the North Pole, where yeah. And then let's talk about manifold. So last session we talked about we said a manifold is a generalization of the notion of a curved surface. So like it looks like a Euclidean space, like the flat Euclidean space locally, but globally it's curved. So like if you look at a tiny patch on Earth, you see it's all flat. So like it's in fact a two-dimensional manifold. And you can look at the figure on the right upper corner. This is a little bit mathematical. Like there's like a map between like a part of like as you can see, like a part of the manifold can be like mapped onto a Euclidean space. Like there is in fact like a homomorphism between these two, and this is a little bit mathematical, but we'll briefly talk about it. This is like a formal definition of manifold. It's super complicated. Like it's saying like there's a locally homomorphic. It's a kind of like Hausdorff topological space that is locally homomorphic to like a subset of Euclidean space, and there are a lot of like mathematical definition. So yeah, so that's why I said different geometry is super complicated with manifolds. And so different geometry is a field of mathematics that deals with geometry using calculus mainly, and a little bit linear algebra or something. And it's and this is like a paper about like differential geometry. There's isn't like a visualization of like the surfaces. It's all theoretical studies. And we talked about metric tensors. It's basically like a measuring machine that can measure distance and angles. For example, you can look at the picture on the left. This is the metric tensor for a sphere. If the metric tensor is given, the surface, the shape of the manifold is given. So this is like a two-dimensional manifold, for example. And wait, and this is you can look at the picture in the middle. Wait, this is the metric tensor for the flat space-time. So it's basically Einstein's special relativity, and also like you can generalize like the inner product and the from matrix tensors. If you have taken multivariable calculus or pre-calc, you may have learned the inner product or the dot product. You can like make it more general, because like in a flat space-time, the inner product is just the sum of the product of each component. But you can make it more complicated. You can, as long as it follows some rules, you can generalize the inner product with the use of matrix tensor. And this is Einstein's field equations. It's basically Einstein's general relativity. So Einstein's general relativity can be summarized into one sentence. People always say it's that space-time tells matter how to move and matter tells space how to curve. Yeah. And as you can see, the R no, the G mu nu is actually the matrix tensor. It's a matrix tensor. It's something describe how the space time is curved. And let's continue with the Einstein's field equation. So there's one solution to Einstein's field equation. I still don't know how to pronounce it. It's Schwarzschild, maybe metric. It's the one solution to one solution that describes the shape of a black hole. And as you can see in here, this is what the line element looks like. It's like the differential element, how it looks like. You can see it's a little bit complicated. So yeah, that's about differential geometry. And let's move on to Schwarzschild black hole. So this is a theoretical prediction from Einstein's general relativity. It's a black hole that is static and also it has neither electric charge nor angular momentum. So like it's stationary, it's not moving and nor rotating. And yeah, it can be described by the Schwarzschild metric. Yeah, this is the metric. And this is also a solution of Einstein's general relativity. And let's talk a little bit about black holes. So definition, a black hole is just a region of space having gravitational field so dense that no matter can or radiation can escape. As you can see, like some pictures in the earlier part of this presentation, like even light cannot escape from a black hole. Yeah, this if you have watched like the movie Interstellar, you may have seen like a visualization of black hole. Yeah, this picture actually really interesting. Yeah. So let's talk about how black holes form were formed. So like if you you guys all know like stars. So when they die, they blast all its outer layers away into space, and what left behind is just a super dense core. And because of the gravity, this core can like the gravity crushes all the core all together, and then a black hole is formed. Yeah, like yeah, it's super dense. Yeah, and in April last year, a black hole, a picture of black hole was captured in the center of the galaxy as Mercer 87, I think. Yeah, and as you can see, all the light were sort of like you can see like a black shadow in the middle. This is like the black hole we detected, and yeah. Let's talk about gravitational waves. So in Einstein in 1916, he published his results about like the general relativity, but he himself did not really believe black hole, even though Schwarzschild has solved his equation. Yeah, and so but his result has, but Einstein's general relativity has shown that massive accelerated objects would disrupt space-time. These accelerating objects, like a black hole, for example, they can disrupt the space-time in a way that waves of undulating space-time would propagate in all directions away from the source. It's like a ripple in the space-time background, right? Like if two black holes are, they move like towards each other, and finally they will vast, no, the way it's you guys all know, right? I don't know how to describe it. Okay, so let's talk about some this stretch the time around the black hole. So this is related to how the gravitational waves were detected. Einstein's general relativity predicted how shows us that time is dilated no it's dilated around a massive object. For example, the black hole. As you are getting closer to the center of the black hole, your time will get slower and slower, and then eventually stop. And as you can see from this picture, right? Yeah. If you're if it falls into the event horizon, the time is completely stopped. Then let's talk about the gravitational waves as we just mentioned. So gravitational waves are just a turbulence in the curvature of space-time generated by accelerating masses. As you can see, the picture on the right, if the two black holes they merge, the wave will propagate in space time, and we can detect it through some complicated engineering technology. There's a 2-minute video, and I'll play this. Can you guys see? Oh wait, I need to reshare my screen.
Yeah.
Yeah. Can you guys see? Okay. Journey of gravitational wave.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes.
Wait, I'm sorry.
Yeah, it's good. So I think you switched to
along the arms.
Yeah.
The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive, it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Okay, let's move on to the, where's my slide? Okay, I found it here. Okay, yeah. And this video shows like how Lego's engineering works briefly. And then talk about the 2020 Nobel Prize in Physics. And Nobel Prize in, the Nobel Prize in Physics this year was awarded to three scientists. As Rohan just mentioned, Dr. Penrose, he's the one that got like half of the prize, right? Yeah. So he has been working on solving Einstein's field equation, and he used many like ingenious mathematical methods and proved that black holes are in fact a direct consequence of Einstein's general relativity. So Einstein himself did not believe that black hole actually exists. Yeah, because he think probably, I don't know, it's like too perfect, and it's not possible in reality, even though it's possible in some theoretical studies. And the last two guys were Gunrose and Gaines. Yeah, and they were working on observing a star in a region called Sagittarius A. I don't know how to pronounce it. Yeah, in the center of our galaxy, and he together with these two, they led to a group of astronomers, and they finally like again verified Einstein's general relativity. So this year's Nobel Prize was awarded to these three scientists. And that's all for today. And thanks for listening. And this is the last lecture on general relativity. And I hope you guys enjoyed. Yeah. Okay. And if you have any questions about the math or the concept in general relativity or like relativity, let me know, and I'm really happy to talk about that. Yeah. I'll stop sharing.
So while you're formulating questions, you can watch the video in the chat. It's about why we see black hole in that way. It's about how like there's a disk of dust, and so it forms the interstellar image that Bohong just showed us. So feel free to email your questions or speak up.
Yeah. Thank you, Alan. Yeah. Yeah. Okay. So, yeah.
All right, stop the recording.
I think I should stop the recording now.